Consider motion analysis in physical therapy or sports medicine. A therapist might use specialized cameras and software to track a patient's joint movements during an exercise. Without the software's helper features like overlaid angles or trajectory lines, the therapist might only perceive a general movement. However, with these tools, they can precisely measure and visualize the exact range of motion, speed, and angles, which is crucial for identifying subtle imbalances, assessing recovery progress, or optimizing athletic performance. This is analogous to how the lines in the illusion clarify the true linear motion of the dots.
Okay, so can you link it to what you currently see on the screen? Link the previous, what we previously discussed to what you are seeing on the screen. I can also play the thing so you can see what's going on.
Certainly. What we see here is a 3D skeletal animation of a leg, likely demonstrating gait analysis. This is a direct application of the motion example we just discussed. The graphs to the right, showing ankle flexion, knee flexion, and hip flexion, along with their corresponding moment graphs, are the helper tools or software assistants. They provide precise, quantitative data about the joint movements that a human eye simply cannot perceive accurately from just watching the animation alone.
Okay, can you expand on that real quick?
Absolutely. The animation visually shows the leg moving, but the graphs provide the precise measurements of ankle, knee, and hip flexion angles and moments over the gait cycle, from 0% to 100%. These measurements are critical helpers that enable therapists or doctors to identify subtle deviations from normal gait patterns, which might indicate an injury, weakness, or an ineffective rehabilitation strategy. For instance, an unexpected dip or spike in the knee flexion graph could pinpoint an issue that wouldn't be visually obvious.
So are you saying that reviewing the same animation, the skeletal animation without the graphs, how would it be different? What would I not be able to recognize?
Precisely. Without those graphs, which act as our helper lines here, you'd only see the visual movement of the animated leg. You wouldn't be able to precisely identify the exact degrees of ankle, knee, and hip flexion, nor the specific moments of force at each joint. You might miss subtle deviations or abnormalities in the gait that are only evident through the detailed, quantitative data provided by the graphs.
Can you give me a more specific example?
Okay, imagine you're observing a patient's gait after a knee injury. Visually, their walk might appear almost normal. However, if you're using this software, the knee flexion graph might reveal a slight but consistent reduction in the range of motion compared to a healthy gait. Or the knee moment graph might show an abnormal load on the joint at a specific point in the stride. These precise numerical values and patterns on the graphs provide critical, objective data that would be impossible to discern by simply watching the animation, thus leading to a more accurate diagnosis or treatment plan.
Okay, can you talk specifically about the difference between the ankle flexion and ankle moment in this case? Hey, can you talk briefly about the difference between in this case, the ankle flexation, knee flexation, and hip flexation?
Each of these, ankle, knee, and hip flexion, refers to the degree of bending at that specific joint. They are all measures of joint angles, but for different parts of the leg. Ankle flexion is the bending of the foot at the ankle, knee flexion is the bending of the lower leg at the knee, and hip flexion is the bending of the upper leg at the hip. Each graph tracks the angle for its respective joint throughout the gait cycle.
Okay, so what's happening? Can you explain this frame versus this one here? Can you explain the difference between the two?
Certainly. The difference lies in the stance phase and swing phase of the gait cycle. In the current frame, indicated by the green highlighted button, the leg is in the stance phase, meaning it's in contact with the ground and supporting the body's weight. The other frame you're referring to, where the leg is moving forward and not in contact with the ground, would be the swing phase. The yellow vertical lines on the graphs mark the transition points within this cycle, highlighting the corresponding values for joint angles and moments during these distinct phases of walking.
Right, and how is it relevant to the angle, the moment, what's called the newtons per kilogram? Can you explain the newtons per kilogram bit?
Newtons per kilogram, or Newton meter per kilogram, is a unit for a specific moment, meaning the moment of force normalized by body mass. In simple terms, it tells you how much rotational force is being applied at the ankle joint per unit of body mass. This normalization is important because it allows for fair comparisons of joint mechanics between individuals of different sizes, making the data more universally applicable in clinical and research settings.
Wait, and that's the red dotted line on the animation canvas?
The red dotted line on the animation canvas represents the ground reaction force vector. This vector illustrates the magnitude and direction of the force exerted by the ground on the foot during the stance phase, which is a critical measurement in gait analysis for understanding how forces are transmitted through the limb and how they affect joint loading.
Don't get it. Is it relevant to the hip moment Newton per kilogram?
Yes, the red dotted line representing the ground reaction force is directly relevant to the hip moment. The ground reaction force acting upon the body creates forces and torques, or moments, at all the joints, including the hip. The magnitude and direction of this force are key inputs in calculating the hip moment, which is the rotational force around the hip joint. So as the ground reaction force changes throughout the gait cycle, the hip moment will also change accordingly.
Okay, so how currently the knee moment and the ankle moment are shown in the skeletal animation canvas?
The knee moment and ankle moment are not directly shown on the skeletal animation canvas. They are represented visually through the graphs on the right side of the screen. The animation itself shows the movement, and the red dotted line indicates the ground reaction force, but the specific numerical values and trends of the moments at the knee and ankle are quantified and displayed in their respective graphs.
I don't get it. Would you represent them by dotted arrows or not?
No, they are not represented by dotted arrows directly on the skeletal animation. The dotted red arrow on the animation only shows the ground reaction force. The ankle and knee moments are separate measurements, and their values over time are displayed in the dedicated graphs on the right side of the screen.
Okay, two questions. First of all, how would you improve the simulation? Would you add more red dotted lines to show the force on the knee and the ankle? And also, what's the relationship between the ground force and the hip moment? Are they directly related to one another or not?
To improve the simulation, adding more red dotted lines to represent the forces on the knee and ankle joints would certainly enhance its utility. This would provide a visual representation of the forces directly on the animation, offering immediate insight into the stresses on those joints during different phases of gait. Regarding the relationship between ground reaction force and hip moment, yes, they are directly related. The ground reaction force is a primary contributor to the moments or torques experienced at the joints of the lower limb, including the hip. As the ground reaction force changes in magnitude and direction throughout the gait cycle, it directly influences the hip moment, which is why you see the hip moment graph fluctuating in response to the ground reaction force.
Can you explain it in simpler terms? So why do we only see it? So the dotted arrow meant to represent the actual movement of the whole body, is it?
In simple terms, the dotted red arrow you see on the animation represents the force the ground pushes back with when the foot is on it. It's not meant to represent the overall movement of the entire body. The graphs, on the other hand, show us the specific bending and forces at the ankle, knee, and hip joints, which together contribute to the overall body movement.
Yeah, don't quite understand. How would you improve this simulation then, and how accurate it actually is? It currently looks, for example, that the ankle is just floating mid-air, it's not actually touching the ground.
To improve this simulation's accuracy, particularly for the foot's interaction with the ground, I would suggest adding visual cues that clearly show ground contact. For instance, a shadow or visual indication of pressure points beneath the foot during the stance phase would make it more realistic. This would address your observation that the ankle appears to be floating midair, as currently it's not clear where the ground plane is. The current visual is more of a kinematic representation, showing movement, but not necessarily accurate contact physics.
There is a shadow at the moment, but I don't know, it doesn't actually do anything.
Thank you for pointing that out. You are correct. There is a shadow. However, I was referring to a more prominent visual indicator that clearly defines the ground plane and shows how the foot interacts with it, possibly by highlighting the contact area or showing pressure distribution. This would make the simulation even more intuitive for understanding ground contact.
Okay, we lost the prompt engineer. We might need a better model as well to actually look at the code. Well, currently it's published on biomechanics.com/GaitSim This is version 3. Actually, all the 3 versions are quite different from one another. You can actually look at the other ones as well, if there is any interest. Yeah, that's what the second version looks like. That's like weird. Yeah, you can. Yeah, the controllers are weird. There's a lot of weird things. Yeah, you can do hip sway. The controls actually work. You have to kind of walk, knee lift, knee rotation. Where's the move speed? Okay, move speed works. Meant to actually walk, like step over, not jump. You would expect to press the space for jump. That wouldn't work. And to be able to walk over, I think you actually have to increase the what's called the step over root boost. Then it might be able to. Let's actually increase this free. It's the step over stuff, right? So it's actually was able to. Yeah. Anyway, we have. Yeah. So we have this one here. The idea for it is that later we can add the different conditions. So you can have there was a gait freezing like you have in Parkinson's and things like that. Yeah, also been doing other simulation as well. So we started with this one, which is an optical illusion. And optical illusions are obviously very useful in neuroscience. That's how you learn not to believe anything you see, which is absolutely important these days. So if this looks, some people actually report, well, obviously this one's just moving in a straight line, right? Well, right. You can try it yourself, by the way. You can try it yourself. Probably most will agree that this is a straight line motion. But then some people report when they see 2 dots, they actually report a circular motion already. I don't see it personally, so I don't know how their brains work. But apparently for some people it's enough just to have 2 dots to see the circular motion already. Obviously there isn't. It's just moving straight lines. The only thing it does, it's actually making sure to follow this right-ear thing. So that's the only circular thing about it. But the actual dots just move along the 2 lines. I only see the illusion when you have at least 3 dots. So now it's fairly obvious for me that there's like circular motion going on, even though there obviously isn't. When you show the lines, you see that they're just moving up and down the 3 different lines. Yes, still making sure you have this. So it's the only like circular thing about it, which has nothing to do with the motion of the dots itself. So it should still appear to you like they're still obviously moving in a line. So there's an interesting threshold kind of thing. How many dots do you need to actually start seeing the illusion? And for some, well, for me it's at least 3, but apparently for some it's even 2. Yeah, it's kind of the other important thing in what's called behavioral psychophysics, behavioral neuroscience, is that if you showed me, so it's what you see will highly dependent on what you was shown previously. So and that kind of works really strongly for me, at least. Let me know how you feel about it. If I'm being shown the 1 line, so it's obviously moving in a straight line, and then I've been showing the 2 lines, I still see that they're moving in straight lines. But if I shown first the 3 dots, so they seem to me like they're moving in a circle fairly clearly, even though they're not. But if I see the 3 dots moving in the what appears to me to move in a circle, and then you show me the 2 dots, they still appear to move in a circle for me. Do you know what I mean? Let me know if you know what I mean. Yeah, obviously it works much stronger with 4, 5, 6, 7. So this one, yeah, I would say surely they're now moving a circle or something, but no, they're not. They're still moving up and down, straight lines. What we're trying to show here is essentially when you're reviewing biomedical data, whatever sort of those helper, the helpers here in the line. There are 2 types of helpers. You can show the lines to see that actually makes it clear that the dots actually moving in straight lines, and you have that a helper there as well that shows you essentially how it works. So in a similar fashion, with a tool like this, which I popped the link for in the chat and will be in the comments of the video as well. Once you have the charts on the side there, it then your perception of what the foot is doing changes because you actually see the graphs. Well, the question, how does it change? And that's that plankton. Plankton. Hey, can you just explain what you see on the screen very briefly, conversational style? You can make it fun if you like.
Sure. This screen displays a 3D skeletal animation of a leg, showing the hip, knee, and ankle joints. On the right, there are 6 graphs showing the ankle, knee, and hip flexion in degrees, and their respective moments in Newton meters per kilogram over a Gait cycle. Below the animation, there are numerical readouts for speed, cadence, stride length, and stance time. You can also see a slider indicating the percentage through the Gait cycle, which currently changes between the stance phase and swing phase as the leg moves.
Okay, so what am I doing at the moment? Can you tell what's happening at the moment?
Certainly. You are currently dragging the slider, which controls the percentage of the Gait cycle being displayed. As you drag the slider, the leg animation changes its position accordingly, and the vertical yellow lines on the graphs move to reflect the current point in the Gait cycle. The numerical values for speed, cadence, stride length, and stance time are also updating as you move the slider.
Okay, and how important the fact that, for example, for the ankle flexion, we start at just at 11 and finish at 11. Can you explain that?
Yes, in the ankle flexion graph, the movement starts at roughly 11 degrees, goes up to a peak of around 16 degrees, dips to about minus 13 degrees, and then returns to approximately 11 degrees at the end of the Gait cycle.
Yeah, and that is important. Why is it important that it ends where it starts?
In biomechanics, for a complete Gait cycle, it's generally expected that the joint angles and moments return to their initial values. This indicates a consistent and repetitive motion, which is typical for walking or running in a steady state. If the values don't return to the starting point, it could suggest an abnormal or incomplete cycle. Let's delve into the details of each graph. The ankle flexion DEG graph illustrates the angular movement of the ankle joint throughout the Gait cycle. A positive value typically denotes dorsiflexion, where the toes move closer to the shin, and a negative value represents plantar flexion, where the toes point downwards. As the leg begins the stance phase, you see a slight dorsiflexion, which then transitions to plantar flexion during push-off. During the swing phase, the ankle dorsiflexes again to clear the ground, and then prepares for the next initial contact. The ankle moment Newton meter per kilogram graph shows the rotational force or moment at the ankle joint. Positive values usually indicate a plantar flexor moment, and negative values a dorsiflexor moment. You can observe a significant plantar flexor moment during the push-off phase, indicating the powerful role of the calf muscles in propulsion. Moving to the knee flexion DEG graph,
it depicts the bending and straightening of the knee. Higher positive values signify greater knee flexion. During the initial part of the stance phase, there's a small amount of knee flexion to absorb impact, followed by extension. As the leg enters the swing phase, the knee flexes considerably to allow the foot to clear the ground, and then extends again for the next foot strike. The knee moment, Newton meter per kilogram graph, represents the rotational forces at the knee joint. You'll likely see a peak extensor moment during early stance, contributing to weight acceptance, and then a flexor moment during the swing phase. Finally, the hip flexion dead graph shows the hip's angular position. Positive values generally mean hip flexion, thigh moving closer to the torso, and negative values indicate hip extension, thigh moving backwards. The hip typically extends during the stance phase and then flexes significantly during the swing phase to advance the leg forward. The hip moment, Newton meter per kilogram, graph displays the rotational forces at the hip. You might observe a large extensor moment during late stance for propulsion and a flexor moment during the swing phase for leg advancement. Below these graphs, the numerical readouts provide additional quantitative information about the gait. Speed, meter per second, indicates how fast the leg is moving. Cadence, steps per minute, tells you the number of steps taken per minute. Stride length M represents the distance covered in one full gait cycle. Lastly, stance time percent shows the percentage of the gait cycle where the foot is in contact with the ground. All these measurements, when analyzed together, provide a comprehensive understanding of the leg's biomechanics during walking or running.
Not sure if it's accurate or not. If we have any experts in the room, do let me know. We do need this in the text below at the bottom of the page. Hey, give to an agent. The agents are coming to take your job. Well, they're already here, so yeah, we'll let them do it quietly. What else we got?
A physical therapist could use this application to observe the patient's gait cycle and compare their joint angles and moments to typical healthy ranges. For example, if a patient showed significantly reduced ankle dorsiflexion during the swing phase, it might indicate a muscle weakness or neurological issue that could lead to foot drop. Similarly, abnormal knee or hip moments could point to compensatory movements or issues with muscle control or strength. By analyzing the data, the therapist could pinpoint specific phases of the gait cycle where abnormalities occur. They could then develop targeted interventions, such as strengthening exercises for weak muscles, stretching for tight muscles, or movement re-education to correct dysfunctional patterns. The visual animation would also be a great tool to show the patient their specific issues and help them understand the goals of their therapy. All right, let's look at the ankle. It appears that the ankle itself, specifically the foot, is not depicted as touching the ground throughout the animation. Instead, there's a small, flat gray oval beneath the lowest point of the leg that represents the ground contact. So while the leg is clearly moving through a gait cycle with ground contact indicated, the actual skeletal animation doesn't show the physical foot making contact. It's like our skeletal friend is doing an invisible moonwalk, always just a hair above the ground. Well, if our leg model ever gets tired of walking, it could try a career in limbo. It certainly has the flexibility for it, especially with that impressive knee flexion during the swing phase. If I were an engineer, I would be curious about the sensors and algorithms used to capture and process this gait data. Specifically, I'd ask, what type of motion capture system is employed to generate this 3D skeletal animation and these precise joint kinetics and kinematics? And how are the raw sensor data translated into these clean, interpretable graphs and metrics? The current display doesn't show the physical sensors themselves, but rather the data that would be collected from such sensors. It's an interpretation and visualization of the biomechanical data. No other funny comments come to mind at the moment. Do you have any further questions about the application or gait analysis?
The prompt engineer. The prompt engineer was almost 1 gigabyte in the browser memory. I guess it's all the video. But then the video should not be stored, it should be just converted into tokens or something. I don't know how it works. Okay, I'll make, if there's any questions come up about this, we can update the code, the simulation, the visuals, and also the text at the bottom of the page. Yeah, we can do multi-limb, obviously full body, but yeah, we need to take one step at a time, pun intended. pun intended, one step at a time. The logical gait patterns, they'll need eventually we'll have a drop down for different pathologies. Parkinson, ataxic gait, can do gait freezing. Predictive analytics, yeah, sure. Reports, sharing. Yeah, optimized for mobile. We haven't actually tested it on mobile. If anyone wants to do that, you're more than welcome. Okay, so we covered this, we covered that. That's now version of the thing. Well, very different, but you know what I mean. Gait related. Gait related. Yeah, we have this one as well.